We'll look at our function f, which is made up of the ordered pairs 1, 1, 2, 4, 3, 9, and 4, 16. If we would like to find f inverse, when you have a set of ordered pairs, the way you find f inverse is you switch the place of the x and y. So 1, 1 will stay 1, 1, but 2, 4 will become 4, 2, 3, 9 will become 9, 3, and 4, 16 will become 16, 4. So we find the inverse by switching the place of the x and y. When we look at our function g and we attempt to find g inverse, if we switch the place of the x and y, we come up with 1, 1, 1, negative 1, 4, 2, 4, negative 2, 9, 3, 9, negative 3. And now we have a problem because we have ordered pairs in which they have the same x element, and g inverse is no longer a function. It doesn't pass the vertical line test or the definition for a function. So what was wrong with g? G was not one-to-one. A one-to-one function is a function in which for every x there's only one y, and for every y there's only one x. And a function needs to be one-to-one before it can have an inverse that is also a function. So when you are trying to find functions, one way that you can tell whether or not that function will have an inverse is you can check to see if it passes both the vertical line test, which is the test for a function, and then if it passes the horizontal line test, which is the test to see if it's a one-to-one function. So if we look at k below, we can tell that k is a function because it does pass the vertical line test. If I want to graph k's inverse on the same coordinate system that we have k graphed, we can just switch the order pairs. 0, 0 will stay 0, 0. 1, 1 will stay 1, 1. But 4, 2 will become 2, 4. And so when I get my graph, it looks something like this. Now note that if I were to draw in the main diagonal y equals x, the graph of k and the inverse of k are reflections about the line y equals x, and that will always happen with a function and its inverse.